Okay, hello everyone. In this video, I would like to show you how to create a model of a plug flow reactor in OpenHydroQual. So I just want to mainly focus on how to use the array feature of OpenHydroQual to discretize your reactor into components so that you can use essentially a series of continuously steered tank reactors to represent a plug flow reactor. So the problem that I will try to solve is sort of like the Streeter-Phelps model. So here are the parameters of the model. So what I have is that I have a reactor with a total length of 100 meters. I'm gonna discretize it into 10 compartments. You can do more um, to get it maybe more accurate results, or if you need higher resolution for some reason. And then so what I have is that I will release the inflow will have a DO concentration of 7 milligrams per liter, a BOD concentration of 20 milligrams per liter. I'll have a flow rate of 37 cubic meters per day. Then the cross-section area of the reactor is 1.11 cubic meters. I made it so that the total residence time is roughly 3 days. And then I have the deoxygenation rate or mineralization, BOD mineralization rate of 0.35 per day, a reaeration rate of 0.6 per day, and then the cross-section area comes out to be 1.11 cubic meters. And I can calculate the volume of each of these compartments. That would be 11.1 cubic meters because the length of each of the compartments is 10 meters. And then I'm going to assume that the saturation DO concentration is 9.5 milligrams per liter. So that's the problem that I want to solve. So let's get started with OpenHydroQual. So the first thing I want to do is that I want to use this component for reactors, representing reactors. So where that is, that's in a plugin called mass transfer. So maybe I have to rename this, not very clear what it means, but anyhow, this does some mass transfer processes and so forth, but also a component called reactor and a constant flow link, which I'm going to use, so just to keep things simple. So I'm going to add this plugin. I'm going to get some blocks and some links and so forth, and then some sources that represent reaeration, even though I'm not going to use them in this example. Anyhow, now what I want to do is that I want to create a series of blocks representing the compartments of the plug flow reactor. What I could do was to maybe just click on this 10 times and then assign all the properties, but that's gonna take a while. There's an easier way with OpenHydroQual. What I can do is that I can go to add objects and then choose this create 2D array. So I'm gonna choose this. Then what I will do is that I need to select here what type of block I need, which is going to be reactor in this case, and then what kind of connector, what kind of link between the blocks I'm going to have. Which I'm going to use this fixed flow. So I'm going to use this fixed flow for the links, and then reactor for the blocks. And then, as I said, I'm going to create 10 blocks. So I'm going to, in the number of grids in horizontal direction, I'm going to specify basically choose 10. And then in number of grid cells, now this tool is actually to create two-dimensional grids, but if I keep the number of grid cells in vertical direction to be 1, it's going to be one-dimensional. So that's all I'm going to do here, and then I click on next, and here what I will do is that I will indicate the volume of, so initial storage is going to be the volume because my inflows and outflows are equal, so the volume is not going to change with time. So the initial storage is going to be the volume of each of the compartments. So if I go back to my drawing, I have here, it says volume of each compartment is 11.1 cubic meters. So that's what I'm going to use. So here I'm going to type 11.1 cubic meters. And then I don't think I need to indicate anything else. So here the bottom elevation is not an issue here. It's not relevant. And then I don't think I have anything else to specify. So I'm just going to click on next. And then the flow rate, I'm going to basically use this value, 37 cubic meters per day. That's my flow rate. So I'm going to come here and say 37. And since I don't have any, it doesn't matter what value is here. I don't have any links in Y direction. So I'm not going to touch anything. I'm just going to click on generate, and what I will get is that I will get 10 reactors that are connected to each other. Now here's what I want to do. I want to do two things. First of all, the water going to flow this way. So I need some inflow into the first reactor. And then I need the water in the last reactor to just go somewhere, right? For that somewhere, what I'm going to use is that I use this fixed head boundary. So that's just a boundary. It's used for whenever I want, the process to terminate, or I don't care what happens afterward, right? So basically I'm going to click on this, and then I'm going to drag it and move it to the end. And then what I will do is that I want to connect this to my last reactor. So what I'm going to do is that I will use this fixed flow link, and then I'll connect my last reactor to the boundary. And what I will do is that the flow rate here is going to also be 37. So I'm going to click on the link, and then if you look at the flow rate, you can just type 37 here. So that takes care of this. That means that in all these links I'm going to have a flow rate of 37. But now I need an inflow into my first reactor. So what I'm going to do here is that I will just select the first reactor, and if you look, there's a constant inflow. And what I will do is that I will just type 37 here. So that's going to be 37 cubic meters per day goes to my first reactor. So this model should work. You know what, let me just save it, even though I don't have any chemical reactions or any processes and so forth. It's just that water enters the plug flow reactor and then leaves. So I can just save this. Let's just call it plug flow reactor PFR. I tried this before, so I have a file called pfr.ohq, which I'm going to overwrite. So now it's a time to, first of all, I can run this, but I'm not going to see anything very interesting. So it's just, if I run it, it's going to be pretty quick. Ran it for 1 day, and then I can click on each of these links, and I should see a flow rate of 37. And then the volume, the storage of the reactors should not change. So it's 11.1, and it stays 11.1 throughout. By the way, what I'm going to do first is that I will just let this, by default the model runs for 1 day, but I want to change that to 10 days. So I'm going to go to settings, general settings, simulation end time, insert a numerical value, and then I'm going to enter 10 days. So that's going to be 10 days. Then let's start adding the constituents. So the first one, I'm going to add BOD. So basically I'm going to right click on the constituents. By the way, I could do it from here too. I need to use this one, chemical constituent. But if I do right click and add constituent, it's going to add a default constituent for me. And basically here all I will do is that I'll call it BOD. Okay, so first I'm going to actually model BOD decay, and then I'll add oxygen, and then I'll add reaeration. So so that's my BOD. Now in order to, first let's test something. So let's say BOD, I haven't assigned any reactions to BOD, so it behaves like a conservative tracer. So but what I will do is that if I click on my first reactor, basically what I can do is that there's this property now added called BOD constant inflow concentration. So this tells me what's the concentration in the inflow, okay, which is sort of going to be my boundary condition. So basically here it says the BOD concentration is 20 milligrams per liter right there, and what I will do is that I'll just make this being 20. Okay, so now I have this BOD that behaves like a conservative tracer, and its inflow concentration is 20. Let's see how things will work. So I'm going to run this. It's going to run for 10 days, and I can look at the BOD concentration at any location. So for example here, it takes some time for the BOD to arrive there. It's going to add some numerical diffusion, obviously because we discretized. If I look at this reactor, the last reactor, the BOD is going to arrive later, so I can compare them. So that's how it works. So the BOD, but anyways, the concentration eventually reaches a steady state of 20 milligrams per liter, and that's what we expect. Okay, now the next thing, I want to add the BOD decay or BOD mineralization. Now in order to do that, first let's add the reaction parameter. That's a cleaner way of doing that, even though I can hard code the parameters, but probably not the best idea. So what I'm going to do is that I'll add the reaction parameter, and then this is going to be my KD. So I'm going to call it KD, and I'm going to enter a value. So let's see what is the value. So here it says the deoxygenation rate, which is the same as BOD mineralization rate, is 0.35 per day. So what I'm going to do is that I'll just enter 0.35 here, and then I can now introduce my reaction. So I go to reactions, add a reaction. I will call this, let's say, BOD mineralization, right? So, and then I need to enter two things. I need to enter the rate expression. Now this is going to be the first order decay, okay? So I'm going to say KD times BOD. That's going to be the rate expression, and then the stoichiometric constant is going to be -1 because the BOD is going to be consumed. Okay, so now what I have is that I have just BOD being mineralized, no reaeration, no oxygen in my model. So it's just a first order decay in a plug flow reactor. Now let's run it and see what we'll get. So I ran it. I can look at what the BOD concentration is. So here it's basically starts from 0 because our initial condition was 0, but it goes up and gets to 18.1, which is slightly less than our boundary condition value of 20, which means some decay has happened. Now if I look at some more downstream blocks, I'll see that I've got some more decay, right? So it's going to be 9.9, and what we know from the theory is that the profile of BOD is going to be exponential. So basically if I paste this and compare them, so this is BOD at my upstream block, this is BOD in my seventh block, sorry, and so on, right? So that's what we have. Now let's next step, let's add DO. Okay, so the first thing I want to do is that I'll just add another constituent. I'm going to call it DO. So that's going to be the dissolved oxygen, and then I need, so here's the thing, I can model reaeration in two ways. One is basically as a reaction, which is what I'm going to do, and I'll tell you why. The other one is to basically use something like this, surface atmospheric exchange or atmospheric exchange. Okay, that's gonna add a source for DO. But then if I use this one, then I will have to assign this source to all of these reactors, because reaeration is going to happen for all of these reactors, and that's going to take some time for me. I mean, it's not hard. I need to click on each of all of these things, all of these blocks, and then indicate the source basically here. So basically I have an external source here, DO, and I need to pick. I mean, now I don't have any source, so it doesn't allow me to pick something, but I have to do it. But I'm going to do it a different way. I'm just going to do the reaeration as a reaction. So I'll show you how to do it. So basically now I have BOD. Now what I'm going to do is that I'll add two more parameters. The first one is going to be my KA, which is the aeration rate, and the value, we decided the value to be 0.6 per day. So I'm going to just type the value to be 0.6 per day, and then the other reaction parameter that I'm going to add is going to be my saturation oxygen concentration. So this is going to be, let's call it DOS, okay, saturation oxygen concentration, and the value here is given to be 9.5 milligrams per liter. So let's just use the value of 9.5 milligrams per liter. Okay, so now let's do a few things. What I'm going to do is that first of all I need to revise this reaction, because the fact is that when BOD is mineralized, oxygen is being used too. So as you can see, when I added the DO constituent, so now it just automatically added this item, this property, to my BOD, to my chemical reaction. So I have a DO stoichiometric constant too. So it's called stoichiometric constant. Anyhow, I will just, this has to be -1, 2, right? Because oxygen is going to be used as BOD is being mineralized. So that's one thing. Then I want to also add my reaeration. Okay, so I'm going to add another reaction. This is going to be, let's call it Reaeration. Okay, the rate expression is going to be basically first order again. So it's going to look something like this. It's going to be Ka times DOS, and this is what we know, that this is a transfer rate expression, right? So DOS minus DO. DOS, we decided it to be 9.5. DO is what is being calculated. Okay, then I need to indicate the stoichiometric constant. So basically for DO is going to be 1, because reaeration is going to replenish oxygen, is a source, and then the reaeration is not going to affect our BOD obviously, so I'm going to keep the stoichiometric constant for BOD to be 0. Okay, now okay, now I need to do a few other things too. So so the BOD concentration in the inflow, the problem says it's 7. Okay, so I'm just going to go here and say my DO concentration is 7. Okay, oh, I'm sorry, I made a mistake. This is not DO. This item is actually the initial concentration, so which I wanna keep it at 0, right? So the constant inflow concentration, that's the inflow concentration, so that's going to be 7. So that's going to be 7, and I think we are all set. Now I'm going to save it. Let's run the model again. So it's done. Now let's look at what happens to, what happens to the BOD shouldn't change, but what happens to DO, we can actually check it. So let's do this one. Now I can look at the DO concentration. So as you can see, our initial value was 0, so then it went up to 5.8. So that's my upstream. Let's say the third block, it went up and then went back down, and then it basically got to a steady state of something like, I don't know, 4.27. Then I don't know, if I go still downstream and look at the DO concentration, now it gets to 3.8, a little less than 3.8, and this one is higher, and so forth. So unfortunately we don't have an ability to look at the spatial profile at different times with OpenHydroQual. You can actually export the data and then plot it yourself, but we can sort of get a comparison. So basically I can do my first block, my third block. I can just paste it here and you'll see it's going down. Now where is my this is the seventh block, still goes down, right? The steady state goes down. Then you have the ninth block, which is higher, so that means we are in recovery stage. The oxygen is being replenished, and then the last block is going to be a bit higher too. So that's, if you look at these things, if you plot them versus distance, you should see something like oxygen sag curve. Thank you for watching, and look for my future videos on different capabilities of OpenHydroQual.